Hi folks, I'm preparing a few video tutorials for the interference fit using 3D Experience finite element platform. Remember, the 3D Experience's FEA solver is actually the Abacus program. So these tutorials are good for people who are either new entirely in 3D Experience or they're Abacus users and are planning to either migrate or occasionally use the 3D Experience version of the Abacus program. Now, the very first one that I do is actually shrink fitting a shaft and a bushing. Okay, so before I do that, let me tell you where the relevant action bar and icons are. So in 3D Experience, the uh, the contact issues are resolved in interactions, and there is an icon here which says contact interference. And here's the icon. And this is the problem that I'm going to be doing. And the main reason I selected this problem is that it's already done by a YouTuber with the Abacus CAE program. So when you look at it, you can actually see what the similarities and differences are uh, as far as the platform and the icons and things like that are concerned. Okay, so these are exactly the same dimensions from that fellow. There are some differences in the way I do this problem and how that gentleman has done it. But notice that the bushing is has a slightly smaller diameter than the shaft, and usually they heat the bushing, expands, put the shaft in it, and then let it cool down. So that's one way of putting these things together. The material for the shaft is the material for the bushing is brass, and the material for the shaft is a lot stiffer. However, because in this tutorial I will be making the shaft as being rigid, of course model it with shell elements and then declare those shell elements to be rigid, I can put a dummy material on it because it's totally irrelevant. Eventually it becomes rigid. Either dummy material, or you can also put the bushing material on it, and then it doesn't matter. It's really it's going to become uh, rigid anyways. Now, if you look at the way these dimensions are, and you look at 1/quarter of this model, 1/4 of this model, you can see the interference here between the bushing and the shaft. The yellow one is the shaft, and this orange one is bushing, and you can see that right now there is 0.3 millimeter interference between the two. Now, because of symmetry, we're going to take only 1/8 of the model, and also I will model the shaft as being a surface and mesh it with shell elements. I have to mesh it because I'm using rigid elements, okay? Later on in another video tutorial, in the next one, tutorial 2, I will make it with analytical rigid surface, which means that I don't actually have to mesh this shaft, but here I do. Okay, and brass properties are given here. This actually should be Poisson ratio. It's not n, it's mu, Poisson ratio. And we assume a friction coefficient of 0.1 between the two surfaces. The mesh is taken because it is made rigid later on. Uh, I need a reference point. The reference point can be anywhere associated with this shaft, with this shaft surface. But for visibility purposes, I put it somewhere out there, but it can be anywhere, including these vertices. Now, I'm going to do this. I'm going to do this problem with two different shell thicknesses. Notice that I mentioned that the shaft has to be meshed with shell elements. And if you're going to mesh it, you need the thickness of the shell, okay? The thickness of the shell, I'm going to try two different values to show you what the reason is. I'm going to try it with 1 millimeter and 0.01 millimeter, okay? Let's see the difference. These are break elements, and these are the four-noded shell elements. So we're going to do this thing together. Now, here's the reason that I mentioned I'm going to use two different thicknesses. When you notice that because the shaft is assumed to be rigid, eventually the inside diameter or inside radius of the hole will become actually the radius of the shaft. Okay? But the radius of the shaft, there is thickness that can be added to it. Half the thickness can be added to it. So all I'm saying is that you've got to be careful if you're using the analytical solution for the contact pressure between for a problem like this. The inside radius of the hole is going to be the radius of the shaft, basically. Okay, the final radius is going to be 25 millimeter. This is the number that we're going to compare our results with. Okay, I'm going to do it with 1 millimeter and show you that actually that's going to cause a problem because there's a lot more overclosure than the actual situation. And then I'm going to come back and do it with the thickness of the shaft, that the dummy thickness to be 0.001. You see that this will give you, with the 0.001, you get something close to that. With 1 millimeter thickness, it's way out of that, basically proportionally higher than this. Now, nothing fancy here, just static analysis, and I have two other slides that I'm going to come back and show you later on, because you can get the result, and then I'm going to show you how you can actually fool the 3D experience to replicate this thing and give you as the full model. And also, when we create our surface contact, in this problem, we have to use both faces to create the surfaces, to surface contact. But in the analytical rigid surface that I'm going to do, it's going to be the next video, one of them, the main surface must be the analytical rigid surface. You can't take the face. Anyway, we come back and look at this thing later on. Okay. All right, so let's go ahead here, and we're going to start an assembly file. So here's an assembly. Let us insert our first 3D part, insert the 3D part. And this is going to be, just so that I can see it, properties. I'm going to call this thing the bushing. Bushing. Okay, and instance name also bushing. These are just for bookkeeping purposes for myself. All right, let's go make it. So we go here to the 3D shape, double click on it, and on that vertical plane, I will sketch something that will be padded to get our bushing. So let's draw this. Let me give it a dimension. This is the outside radius of the bushing, which is 50 millimeters. Now I'm going to draw the inside one, which is a little bit less than the radius of the shaft, as we mentioned. So this is going to be 24.7. So there is a essentially there is almost 3.3 millimeters of radial interference. Okay, there's a little bit more if you consider the thickness of the shaft into consideration, but let's not worry about that right now. Another one. Okay, exit. Now I want to make a solid part out of that. Ordinarily, I go to the part design in order to do that. But notice that even if you're in generative shape design, there is an option here which says volume. If you want to create a volume, you can do it right there. This is not the same as a three-dimensional part, but it's good enough for our purpose. So the choice is yours. You can go to part design and do the problem, or you can stay here and do even the volume right there. So volume, you select this in the other direction, 10 millimeters, half the original thickness of the bushing. And while we're at it, let's go ahead and apply our material to that. So we go to tools, let me create a material here. And I'm going to call this thing bushing. Bushing. And today is October 25, so that I can find it there. 2023. Say OK. So it's going to go into database and show me all the stuff that I have here. If you cannot, right here, see that bushing October 25, 2023. So apply, and I'm going to apply it to that. Of course, we have to input the data. So structural, abacus multiphysics, mechanical, elasticity, elastic, and that is 100,000 MPa or 100 GPa. 100 GPa, and Poisson ratio is 0.34. 0.34. Now, I can also create a dummy material later on, but since the dummy material is going to be applied to shell, which is going to become rigid later on, I'm not going to do that. I'll just apply the bushing to that shaft also. All right, that's good. Do a quick save. And now we're going to insert our second 3D part. Right click, insert, 3D part, another one. I'm going to call this thing shaft. Okay, and shaft. Okay, we're going to make it. It's just a surface, so double click on this thing. I'm already in generative shape design, which is good. I can create surfaces. So on that vertical plane, I will sketch an arc, which is 0.25 millimeter, quarter of a circle, which is 0.25 millimeter in radius. Okay, so let's give it a dimension, 25 millimeters. Oops. Oh, I didn't mean to fix this thing. Let me delete that. Dimension this. Right, 25 millimeter. Now notice that if you look close enough, the shaft is already inside of that bushing. Okay, good. Exit and extrude it. It's a surface. We can extrude it 200 millimeter, 100 millimeter. But this is in the wrong direction. I want it to go in the other direction. Just nicer for me. All right. And while I'm here, I'm going to create a point there, and that point is going to be the reference point for this later on rigid set of elements. So essential point. Okay, let me give it the coordinates. So for example, x of minus 100 and y of let's say 40. Z is 0. So there is a point here which later on is going to be used for the controlling the rigid element. Now, apply material. I can create a dummy one, or I can actually go ahead and use the same thing here. So, for example, pick using the tester, pick that material, and then apply it to this other guy. That's one way, fancy way of doing it. Otherwise, you go and apply the usual way. Here, bushing, etc. Good. So this is pretty much it. As far as the model is concerned, this is it. So now we're going to go, I'm going to go all the way to the top. Notice that on purpose, I'm going to go all the way to the top because I'm going to create my elements at the assembly level instead of creating the elements at the part level and then put it in there, etc. I'm going to go all the way to the top and then either do this either go to structural model creation, that's one way of doing it, or it's entirely up to you. You can say right click, insert uh, representation, and then when it asks you about representation, you say finite element model. No, I'm going to go do it this way. Less things to worry about. It's an empty one. And it says there are two parts here. Which ones do you want to be included? So I want both of them to be included. If you follow the other route, then you have to do this thing manually yourself, which is fine. So it's right there, but it's empty. So now we're going to go to meshing. Meshing. Incidentally, that reference, the gentleman is actually partitioning that piece. I didn't do that. I didn't partition it. Okay. It's a simple problem. We can do it like this. So we're going to go and do a sweep mesh here, except that I don't want to sweep it in this direction. I want to sweep it in this direction. So I say manual source. Let me remove these. For the first surface, I select this. And for the second surface, I select that. So it's going to be sweeping like that. And there's 20 layers. The 20 layers like that. And mesh size is 1 millimeter. So we're going to get our mesh right there. Okay, let's apply properties to it because it doesn't know what material it is. You click on this solid section on the properties tab, solid section. You select that part. You can do it from the tree or you can do it from the screen. Notice that it picked the bushing material. Okay, good. Now we're going to mesh this surface. So under the mesher, the nice surface quad mesher right there, and the thickness is not the thickness, but the size of the element, I'm asking it to be 1.5 millimeter. Eventually it becomes rigid, of course, for noded. So we go mesh it. Okay, good. And now we have to apply properties to it. So we're going to go shell section. On this part, on that surface, notice that the bushing material is picked, but remember that this is dummy because eventually it's going to become all rigid. So 1.5 millimeters, 1.5 millimeter, not 1.5, 1 millimeter, because what I want to do is I want to show you the effect of doing 1 millimeter versus uh, something smaller, okay? 1 millimeter. All right, good. So the model has been created. Now, the only thing is that I want to make these things rigid, okay? So in order to do that, this is what you do. You go to the abstraction tab. There is rigid body. It says, take the support. The support is that surface, extrude. And the point, the reference point specified. I selected that, and this is going to be my reference point. So whatever apply here is going to apply to the entire this. For example, if I clamp this thing, the whole thing is going to get clamped. Okay, good. So let's notice that abstraction has been selected right there, or has been made right there, and save. Okay, and now we're going to go and create our scenario. So you go there, structure model scenario, structural scenario creation, structural scenario creation. There is the finite element model that I created. I want to select it, 17123, 17123, and it's a structural problem. Notice that there is a red check mark here, no procedure. You click on the procedures tab and then select the static. The only thing I'm going to do, I'm going to start with a smaller initial time increment. That's it. Everything else is default. Okay? This is a static problem. Nonlinear geometric effect is already included by default. Okay, so under boundary conditions, now remember, these things are planes of symmetry. This plane, and the one in the back. That YouTube reference is going to, just to show you how things are done, it creates a node set here, creates a node set there, create a node set there, call it X sim, Y sim, Z sim, and then apply the symmetry boundary condition. I'm not going to do that because there's a very nice feature here under boundary conditions. If you, okay, here, under boundary condition, if you expand, there's something called planar symmetry, okay? So I click on it. This is a planar symmetry. Say okay. Unfortunately, you have to do this thing 3 times. This is a planar symmetry. Oops. Do I have 3 of them? I better have 3 of them. Okay, so let's check this. Yeah. First one, second one, third one. Good. All that means is that there is no displacement perpendicular to it. And because this is rigid, I don't have to put any symmetry conditions on these edges. So finally, I'm going to clamp this point. You have 2 choices. You can either clamp it, that point, or just say fixed displacement, no translation, no rotation. It's entirely up to you. Let me do this. So this is the support. Support is that reference point. No translations and no rotations. It's just basically clamped. Good. We now go and create our interaction. So interaction, yeah. So there is a coefficient, friction coefficient, right? So I go and, by the way, let me unpin this. I don't want to see this thing. Good. So interaction, where is that? Interaction. So that I don't see that other stuff. Where is that? First, we define the coefficient of friction. So under right here, contact property 1. I'll call this thing my contact property because just to tell you that this is a name. My contact property, friction, specify friction coefficient 0.1. Okay, now we have to create a surface to surface contact. So let me get rid of these elements. Right click, mesh visualization. Don't show me the element, just show me the parts. Okay, so we go here, surface-based contact. You click on it. So for the main surface, we use the surface of the shaft. And for the secondary surface, we use the surface of this bushing, okay? We don't want to tie it. This is going to be interference fit. Actually, it's contact really, so don't do the tie. And we say okay. Good. And now there is this icon here, contact interference. So let me remind you where we are. It's right there, right? So contact interference. It says, where is your surface contact? It's the one that we created. So you can either do it from, I know it's kind of hard to do it from the screen. So let's go to our static step, or maybe on the interaction. On the interaction is this thing that we created, surface-based contact. See that? It says surface contact, this guy. It also appears in the tree down here, probably. Yeah, but you can't pick it from there. That's the thing. You have to pick it from here, surface. And then it picked it, say OK. And let's update this because there is some updates required there. I just feel more comfortable if the updates are taking place right there. Very good. And that's pretty much it. We save this thing. All right. Now, we're going to go to simulate. Let's do a quick model and scenario check. No problem. Do a quick simulation check. Okay. This is not running, it's just checking stuff. If there are some obvious message errors or things that you left out, they may pop up here in these checks. It's similar to the data check that you do in the advocacy. Okay, this is done. very much. Yep. And now we're going to run it. So it will run, however, just be careful because uh, the actual running takes place only when you get the dialog box here and you click on OK. Right now it's communicating maybe on internet and things like that because this is all cloud-based. So, and it's going to be very quick, but it will not give you these values from the analytical solution. You'll see what we have to do. We don't do that. Now, when I click this thing, then it's going to run, start running. And if you click on iteration, it gives you the counterpart of what you call monitor in the CAE program, Abacus CAE program. Okay, started running. So it's going very quickly. And it's done. So close that. Let's see what we've got. Let's look at the von Mises stress. This is the initial increment, which obviously there's no load on it, nothing there. But if you go to the final one, there. This is the von Mises stress. As a matter of fact, let's look at the contact pressure. Okay, you've got to be careful here because this shows you the contact pressure at different levels where this overclosure is being resolved. So that's initially, of course, nothing. And then the answer is this last one. In other words, after the overclosure has been taken care of, what is the contact pressure, which is about 1600 megapascal. Now, wait a minute, that is not 1600 megapascal. The reason is that the shell thickness in this run was 1 millimeter. So actually, the amount of overclosure is half of that, which is 0.5, plus the original 0.3, which is 0.8. What I'm saying is that if you take this number, uh, this overclosure is not 25 minus 24.7. It's actually, but anyway, let's move on and let's change the thickness and run it again. That's very easy. So you go here, you go to shell section. Instead of 1 millimeter, we put down 0.001 millimeter. Okay. And now we're going to run it and compare the contact pressure with what we've got in that calculation. We'll see. It's not running yet. It will in just a minute. Once you get that dialog box, it's going to converge very quickly because it's a very simple problem. In the next tutorial, I will come back and repeat this with that shaft being modeled as an analytical rigid surface. Now, of course, there we don't have this issue of shell thickness and things like that. You say, okay? And now it's running. Give it some time. All right, starting simulation solver. It's going to go through very quickly because this is a simple problem. All right, and now we're going to look at the same thing, except that, remember, the last increment, okay? Say close. 660 almost, okay, right? So this is a lot closer to this number. Now I want to show you actually how you go about uh, showing this thing in its full configuration. So here's the steps that you have to follow. In the results, we are in the results, display results option, and then you check these boxes. Okay, so let's go ahead and do that. So we are in results, we are in display, now we're in display, and results options, and we say under this tab, you see that? Model symmetry, check the box and say, show me all replications of this. There we are. Okay, so this is just to fool it so that it thinks that it has done the whole problem. There's one more thing I want to do. Let me actually put this thing back where it was. Let me say, don't show me this. Now I want to show you something about this business of, if I try to hide this thing, it won't let me do that. Here's what you do. You create a display group. That's what display groups are used for. Create different views, okay? Okay, so you select, you click on it, see that? You click on it. Here's the group, display group, and I want to make one. Create a new display group. I'll call it display group 2. I say okay. So if you and check mark, green check mark, if you double click on this, it says, okay, what do you want to include in your display group? In this particular situation, and you can do different things, but in this particular situation, I want to just include the bushing. That's it. Just the bushing, no shaft. So click on the shaft and then say replace. There we are. And we say okay. Close. If you double click on this thing, only the bushing is shown. If you double click on this first one, everything is shown. Let's go back, double click on this, turn it around. There we are. Okay. All right. Let's say you want to do another one with, for example, one mesostress. So you click on this, display group, add, group 3, okay, mark, click on this, says, what do you want to put in there? Well, I want, for example, the shaft. Replace that with the shaft, and there we are. Okay, you go to this one, it's going to be everything. You go to this one, it's going to be the bushing, and to this one, it's going to be the shaft. So these are very useful, but you have to practice with it to get the hang of it. That's pretty much it. Good luck. Tutorial 2 is going to be repeating the same problem with analytical rigid surface. So I don't have to mesh this thing, and I don't have to worry about the thickness of the shell and things like that.